We built the most powerful machine in human history. Not a weapon, not a rocket, a ring. A 27-kilometer ring of superconducting magnets buried 175 meters underground beneath the border of Switzerland and France. We spent $13.25 billion on it. We recruited over 10,000 scientists from 100 different countries. We cooled its interior to minus 271.3 degrees Celsius, colder than the void of outer space, and we aimed it at the smallest things in existence. The goal was simple: smash particles together so violently that we recreate the conditions of the universe 1/trillionth of a second after it was born. Look at the wreckage, map it, understand the rules. We thought we knew exactly what we would find. We expected to confirm a theory we'd spent 50 years building. We expected the debris to match our equations perfectly. We expected nature to obey, and for a while it did. We found the Higgs boson in 2012, the so-called God particle, the last missing piece of our master equation. Scientists worldwide wept with joy. Textbooks were rewritten. Nobel Prizes were handed out. We thought we were done. But then we kept looking, and the machine kept running, and the data kept coming in. And somewhere deep inside that mountain of numbers, buried in the collision records of trillions of proton impacts, the physicists started finding things that do not belong, things that the equations say cannot exist, things that point not just to new particles, not just to new forces, but to something so structurally wrong with our understanding of reality that some researchers at CERN have quietly stopped calling it an anomaly. They're calling it a signal, not a signal from another civilization, not a radio wave from a distant star, a signal from somewhere the laws of physics should not allow anything to come from, a message written in the wreckage of shattered protons that says, everything you built your world on is incomplete, and the thing you are missing is not small, it is not a rounding error, it is not a smudge on the data, it is a door, and it appears to be open. Here is why that terrifies the people who study it for a living. Here is why the physicists who have dedicated their lives to this machine are not celebrating. And here is what it means, not just for science, but for the ground beneath your feet, the air inside your lungs, and the atoms your body is made of right now. Because what CERN found doesn't just break a theory. It breaks the wall between what we thought was everything and what might be waiting on the other side. There are 7 layers to this discovery, 7 separate cracks in the foundation of reality that the data is showing us. And by the time we get to the 7th, the question will no longer be whether our picture of the universe is wrong. The question will be whether there was ever a picture at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. The first crack. The particle that should not decay that way. Let's start with what should have been a routine measurement. Inside the Large Hadron Collider, 2 beams of protons travel in opposite directions at 99.9999991% of the speed of light. When they collide, the impact is so violent it briefly generates temperatures 100,000 times hotter than the center of the sun. For 1/trillionth of a second, the ordinary rules of matter dissolve, and raw energy transforms into exotic particles that vanish almost as quickly as they appear. Most of these particles behave exactly the way the standard model predicts. They decay into predictable products. They leave predictable tracks. They confirm the equations we've written. But one category of particle has been misbehaving for years in a way that has slowly escalated from curious to deeply alarming. It is called the B meson, and it is breaking the most fundamental rule of particle physics. Here is why this matters. The standard model, the master equation that governs everything from how electrons orbit atoms to how the sun burns, makes an ironclad prediction about the B meson. When this particle decays, it should produce muons and electrons in equal numbers. Not approximately equal, exactly equal. The math is precise to 9 decimal places. It is one of the most confident predictions in all of physics. It is called lepton universality. And if it holds, it means that all electrons and all muons are treated identically by the forces of nature. It means the universe is blind to the difference between them. In 2021, 2023, and again in new results published in December 2025, the LHCb experiment at CERN measured this ratio. They looked at billions of B meson decays, and they found something wrong. The muons and electrons are not appearing in equal numbers. The ratio is off. It deviates from the prediction in a way that has now crossed the threshold of 3/8 sigma, meaning the probability that this is a statistical fluke is roughly 1 in 15,000. In particle physics, 5 sigma is the gold standard for a discovery. 3.8 sigma is the red flare sent up before the discovery is announced. But here is why you should feel something colder than scientific curiosity when you hear this. Lepton universality isn't just a number in an equation, it's a load-bearing wall of the standard model. It's one of the reasons we believe the forces of nature are symmetric. It's part of why the universe behaves consistently across all of space and time. If leptons are not universal, if muons and electrons respond differently to the forces around them, then there is a force, or a particle, or a dimension that the standard model doesn't know about. Something that pushes on muons harder than it pushes on electrons. Something invisible to our current instruments, but real enough to bend the data. Think about what that means at the level of your own body. You are built out of standard model particles. Every atom in your body follows these rules. Your neurons fire using these interactions. Every chemical bond in every protein in every cell of your biology is governed by the forces the standard model describes. If there is a force operating on matter that we have not found, not mapped, not named, then we don't fully understand what you are made of. We don't fully understand what you are. Think about the precision involved. This is not a rough measurement. This is billions of recorded B-meson decays, analysed by teams of hundreds of physicists using calibration procedures refined over years. The systematic uncertainties, every known source of measurement error, have been checked, rechecked, and reduced to their irreducible minimum. The signal persists after all of it. The B-mesons keep dying wrong. Here is the deeper implication. The B-meson doesn't care about our equations. It doesn't know it is supposed to decay symmetrically. It simply obeys the forces acting on it at the moment of its decay. If the ratio is off, it is because a force is present at that moment that our theory says shouldn't be there. A force that is real. A force that has been operating on every B-meson decay in every collision in the history of this experiment. A force that has been right there in the data, hiding in the ratio of muons to electrons, waiting for us to count carefully enough to notice it. We thought we had completed the map of fundamental physics, but the B-meson keeps pointing at a blank space on the map where something vast and unnamed is hiding. And that's just the first crack. It gets worse. The second crack. The muon that wobbles wrong, the muon. You probably don't think about it much. Neither did physicists, until it started doing something impossible. A muon is essentially a heavy electron. Same charge, same spin, but about 217 times heavier. It appears briefly in cosmic ray showers and in particle colliders and then decays almost instantly. It lives for about 2.2 microseconds before turning into an electron and 2 neutrinos. In the grand theatre of particle physics, the muon is a supporting character, a minor player, until it started lying. Like any spinning charged particle, a muon behaves like a tiny magnet. The strength of that magnetic behavior is described by a number called the G-factor. Quantum mechanics predicts the G-factor of the muon to extraordinary precision. It accounts for every known particle and force. It is one of the most precisely calculated numbers in all of theoretical physics, computed to 11 decimal places by accounting for millions of quantum corrections, each one smaller than the last, each one corresponding to a specific virtual particle flickering in and out of existence in the quantum foam around the muon. The measured value should match the theoretical value down to 11 decimal places. It doesn't. The discrepancy is small by everyday standards. But in physics, a discrepancy at 11 decimal places isn't small, it's a scream. In 2021, Fermilab published results from the Muon G2 experiment showing a deviation of 4.2 sigma from the standard model prediction. In June 2025, the final dataset was published. 6 years of data collection, the most precise measurement of any particle property in human history. The deviation held. The muon is wobbling in a magnetic field more than it should be. Consistently, reproducibly, across every run, more, not less more. Here is the logical chain that makes physicists lose sleep. The G-factor calculation works by accounting for every particle that can briefly pop in and out of existence near the muon, a quantum foam of virtual particles that flicker into reality and slightly push the muon's magnetic moment in specific directions. Every known particle's contribution has been calculated and included. The sum of all those contributions gives you the predicted G-factor. When you measure the actual G-factor and it is larger than the sum of all known contributions, only one explanation is consistent with physics. Something is pushing the muon that we haven't included. Something exists near the muon that the standard model doesn't know about. Some particle, or perhaps some entire class of particles, that is flickering in and out of existence in the muon's environment, carrying force, exerting magnetic influence, and then vanishing back into whatever sector of physics it came from before we can catch it directly. You cannot fake magnetism, you cannot fake angular momentum. The muon is not confused. The muon does not lie. The muon is telling us, in the most precise measurement language available, that its environment contains something the standard model refuses to admit exists. And the something has been consistent across 6 years and 1 trillion measurements. Now look at the two anomalies together. The B meson is decaying wrong. Muons are being suppressed relative to electrons. The muon is wobbling wrong. Something invisible is adding to its magnetic moment. Both anomalies involve the muon behaving differently from prediction. Both point toward a new particle or force that interacts with muons in ways the standard model doesn't model. The class of theories that explains one also explains the other. They are not separate problems. They are two symptoms of the same unknown disease, and the disease is something real. Physicists have a name for particles that could explain both simultaneously. They call them Z-prime bosons, heavy, neutral force-carrying particles that would couple to leptons in ways that break the symmetry between muons and electrons, and would also contribute virtual corrections to the muon's magnetic moment. A Z-prime doesn't exist in the standard model. There is no room for it. It would require new mathematical structure, new symmetries, new sector of physics, but the data is pointing at it. Two different experiments, measuring two different quantities, converging on the same blank space in our theory. Something is there. The third crack, the energy that comes from nowhere. Let's step back from particles for a moment and look at the machine itself. The LHC accelerates protons to 13.6 TeV, trillion electron volts. At that energy, we are recreating conditions that have not existed since the first fractions of a second after the Big Bang. We are looking at physics that the universe has not experienced for 13.8 billion years, and we are carefully measuring everything that comes out of those collisions. Here is what we expect. We expect conservation of energy. This is the most basic, most ironclad law in physics. Energy cannot appear from nothing. Energy cannot disappear into nothing. In every collision, the total energy going in must equal the total energy coming out, always. Without exception, it is not a law that admits exceptions. It is a law that defines what we mean by a law. Except that in specific categories of high-energy collisions at the LHC, the energy doesn't balance. Not by much, but by enough. There is a systematic deficit in specific decay channels, a small but persistent gap between the energy measured going in and the energy measured coming out. The detectors are extraordinarily precise. Their calibration is the product of decades of refinement. The teams running the analyses are some of the most technically skilled scientists alive. They have spent years ruling out systematic errors, instrument drift, and misbration. They have checked the energy balance against auxiliary measurements, against independent detector systems, against theoretical predictions from every angle. The energy is still missing. In the standard model, there is one known particle that can escape a detector without registering, the neutrino. Neutrinos have almost no mass and zero electric charge. They interact so weakly with normal matter that a trillion of them pass through your body every second without leaving a trace. When a collision produces neutrinos, they escape the detector carrying energy we cannot directly measure, but we can infer their presence and their momentum from the missing energy budget. We account for neutrinos in every calculation. We are very good at accounting for neutrinos. The missing energy in these specific channels is not consistent with neutrinos. The geometry is wrong. The angular distribution is wrong. The energy spectrum is wrong. The missing energy doesn't point back to the interaction vertex the way neutrino emission should. It doesn't carry the transverse momentum signature of a two-body decay. It has a profile that doesn't match any standard model particle. Something is being created in the highest energy collisions on Earth. And then it is leaving, not through the walls of the detector, which are designed to stop almost anything, not through the superconducting magnets. It is simply disappearing, stepping outside the range of everything our instruments can touch. Think about what it means for energy to disappear from the LHC. The detector is a cathedral of measurement. The Atlas detector is 46 meters long, 25 meters high, and weighs 7,000 tons. It has 100 million individual sensor channels. It is designed to capture every particle produced in a collision, to leave nothing undetected. Engineers spent decades ensuring that energy could not escape without leaving a trace. The calorimeters trap every photon. The muon systems capture every muon. The tracking systems record every charge particle trajectory. Every cubic meter of detector has been accounted for, and energy is still leaving. Not through the detector, through something else. Through a channel that the detector architecture assumes doesn't exist, because the standard model says it doesn't exist. A channel where particles produced in a collision propagate away from the interaction point in a direction that the detector cannot follow. A direction that is not up, down, left, right, forward, or back. A direction into dimensions the detector doesn't have sensors for. A physicist named Jan Judice, who heads CERN's theoretical physics department, has called this kind of signature, missing energy inconsistent with known standard model particles, the most exciting thing we could possibly see. Because missing energy that cannot be explained by known physics has only one coherent interpretation in the theoretical frameworks that physicists have developed to handle this scenario. The energy is going somewhere else. Not somewhere else in this room, not somewhere else in this solar system, somewhere else in the architecture of space itself. The fourth crack. The dimensions we cannot see, this is where we have to ask you to set aside your intuition, because your intuition is a liar. You believe you live in 3 dimensions. You can move forward and back, left and right, up and down. You've never experienced anything else, so you assume there isn't anything else. The assumption feels so obvious it seems like an observation rather than an assumption. But it is an assumption, and it has no mathematical necessity behind it whatsoever. The equations of general relativity don't require 3 spatial dimensions. String theory requires 10 or 11, M theory requires 11. The holographic principle requires the bulk of information to live on a 2-dimensional surface. Kaluza-Klein theory proposed a 5th dimension in 1919 and the math worked beautifully. It unified gravity and electromagnetism in a single framework that physicists still study today. The question has never been whether extra dimensions are mathematically possible. They are. The question is whether they are physically real, and that is a question CERN can test. What would an extra dimension actually do to the physics at the LHC? Here is the key insight, and it is the one that makes the missing energy results so alarming. If extra dimensions exist at or near the scale of a few femtometers, roughly the size of a proton, then particles created in LHC collisions could propagate into those extra dimensions. They would carry energy and momentum into a region of space that our detectors literally cannot access. Not because the detectors are bad, because the detectors are 3-dimensional objects in a potentially higher dimensional space. They can only sample what happens in the 3 dimensions they occupy. The energy would not be destroyed. It would not violate conservation. It would go somewhere our instruments have no coverage for, and the signature of its departure would be exactly what we see, a systematic deficit in the energy balance of specific high-energy collisions. There is a specific class of particles predicted by extra-dimension theories called Kaluza-Klein gravitons. These are gravitons, the hypothetical carriers of gravity, that have been given extra momentum by propagating through a higher dimension. From the perspective of our 3-dimensional detectors, they appear as missing energy. They step sideways out of our spacetime, carrying energy into the extra dimension, and our instruments have nothing to register. No track, no energy deposit, just an absence where there should be presence. Does this sound familiar? There is more. Lisa Randall at Harvard and Raman Sundram propose models in which our entire universe is a membrane, a brain, floating in a higher dimensional space called the bulk. In their models, all the particles we know are confined to the brain. The quarks, the electrons, the photons, the W and Z bosons, all of them are stuck here on the surface, unable to propagate into the bulk. But gravity is different. Gravity in these models is not confined to the brain. It leaks, it propagates freely through the bulk. It dilutes into the extra dimensions. And what we experience as gravity in our universe is only the thin residue of a gravitational force that is spending most of its strength somewhere we cannot see. This would explain one of the deepest, most embarrassing mysteries in fundamental physics, the hierarchy problem. Why is gravity so much weaker than the other forces? The electromagnetic force is 10 to the power of 36 times stronger than gravity. That number has no natural explanation in the standard model. To make the standard model consistent with that number, you have to fine-tune your equations by hand to a precision that has no physical justification. Physicists call it fine-tuning, and they are deeply uncomfortable with it, because fine-tuning without a mechanism is not an explanation. It is a confession of ignorance dressed up as a number. But if gravity is leaking away from our brain, the hierarchy problem dissolves. Gravity isn't weak, it's diluted. Most of it is elsewhere. We only feel the fraction that doesn't escape into the bulk. The enormous apparent weakness of gravity is not a fundamental property of nature. It is a geometric artifact of living on one surface of a higher dimensional architecture. And here is the part that makes physicists uncomfortable at professional gatherings. If gravity can leak from our brain to the bulk, it can also carry influence from other things in the bulk into our brain. A massive object existing on a different brain, or in the bulk itself, would exert gravitational influence on our brain, even though we could never directly detect it. We would feel its gravity but never see the thing producing it. We would invent a name for its gravitational effect and call it dark matter. Think about what that reframing means. Dark matter, the invisible substance that accounts for 27% of all the energy in the universe, that holds every galaxy together, that shapes the large-scale structure of the entire cosmos, might not be matter in our universe at all. It might be gravitational influence bleeding through from something we cannot see, in dimensions we cannot access, from a neighbouring structure that is physically present in the bulk while being completely invisible to every instrument we have ever built. We have been mapping the shadow of a continent we've never visited, and calling the shadow dark matter because we didn't know what else to name it. The fifth crack, the antimatter that refused to die here, is a question so fundamental that it should terrify you. Not in a philosophical sense, in a physical, mathematical, existential sense. Why are you here? The Big Bang did not create matter. The Big Bang created energy, and when energy transforms into particles, it always creates them in pairs, one particle and one antiparticle. Always, without exception, every time. This is one of the most rigorously tested laws in all of physics. It's called CP symmetry, and it holds in every controlled experiment we've ever done in a laboratory, which means the Big Bang should have created exactly equal amounts of matter and antimatter. Which means when the universe cooled enough for matter to form, every particle should have found its antiparticle partner. They should have found each other and annihilated each other completely. Matter and antimatter touching produces pure energy, a gamma-ray burst and nothing more. Zero matter, zero antimatter, just radiation spreading through an expanding void. The universe should be empty, just a cooling, thinning fog of radiation spreading through infinite space. No atoms, no stars, no planets, no chemistry, no biology, but instead you are here, reading this. Made of matter that should not exist, because the antimatter that should have deleted it apparently wasn't there. For every billion pairs of matter and antimatter that should have been created in the Big Bang, exactly one extra particle of matter survived. 1 in a billion. Not 2, not 0, 1. And those 1 in a billion leftovers, those lone survivors of the cosmic annihilation, are every galaxy you have ever seen, every star that has ever burned, every planet that has ever formed, every ocean that has ever covered a rocky surface, every living cell that has ever divided, every thought that has ever been thought. One extra particle in a billion. That is the entire history of existence. That is the entire story of the universe. We have no idea why. The standard model predicts matter-antimatter symmetry. Reality shows matter-antimatter asymmetry. This gap is not a small discrepancy. It is not a rounding error. It is the reason existence is possible. It is the entire universe sitting on one side of a scale that the laws of physics say should be perfectly balanced. And we have been staring at this imbalance for 60 years without a satisfying explanation. CERN is supposed to answer this. The LHCb experiment, the Large Hadron Collider beauty experiment, was specifically designed to measure CP violation, the tiny asymmetry in how matter and antimatter decay. If we can measure that asymmetry precisely enough, we can trace it back to its source. We can find the law of physics that tilted the scale. We can identify the force that looked at equal amounts of matter and antimatter and decided, once and once only, in the first microsecond of time, to let one particle of matter through. Here is what they found instead. The CP violation they are measuring in certain boson decay channels is larger than the standard model predicts. Not just by a little, by enough to suggest that whatever tipped the cosmic scale in favor of matter is not fully described by our current equations. There are contributions to CP violation, contributions from physics we have not written down, that were active in the first microsecond of the universe and pushed matter above antimatter by a hair that became everything. Think about the chain of causality. Some force, some particle or interaction that we have not yet found, existed in the first microsecond after the Big Bang. It was active for an instant. It was present at energies and densities that no collider has yet recreated. It introduced a tiny asymmetry into the otherwise perfect balance of matter and antimatter. And then, as the universe cooled and expanded, that asymmetry froze out. The force became inactive. It receded into whatever sector of physics it inhabits. It left no other direct trace. Except that one extra particle in a billion survived. And 13.8 billion years later, that extra particle is a galaxy, is a star, is a planet, is a cell, is a brain capable of wondering about its own existence. CERN is now finding in the meson decay data hints that this force is still visible, still leaving faint echoes, still producing measurable deviations in the way matter and antimatter behave. The CP violation excess is not an artifact of measurement error. It is a fingerprint left by whatever caused the universe to choose matter over antimatter in its first moment of existence. We are reading the handwriting of the force that created everything, and the handwriting doesn't match anyone in the standard model's registry. The sixth crack. The Higgs field is sitting on a ledge. We need to talk about the ground beneath your feet. Not metaphorically, the literal ground, the actual physical substrate of reality, the reason atoms don't fall apart, the reason matter has mass, the reason you have weight. It is called the Higgs field. It permeates every cubic centimeter of space in the known universe. It is everywhere, here in this room, inside the sun, between galaxies in the deepest void. You move through it right now the way a fish moves through water, completely unaware of its presence, because you have been inside it your entire existence. You cannot feel it because every particle in your body is already calibrated to its value. It is the medium your reality is made of. The Higgs field gives particles their mass. Without it, electrons would travel at the speed of light and never settle into orbits. Without it, quarks could not form the bound states that make protons and neutrons. Without it, atoms would never form. Chemistry would be impossible. Biology would be impossible. You would be impossible. Everything that makes you real, every chemical bond, every protein fold, every electrochemical signal in every neuron is a downstream consequence of this field having the specific value it has right now, at this moment, in this room, in your body. And here is what the data from CERN is telling us. The Higgs field may not be stable, it may not be at its lowest possible energy state, it might be sitting on a ledge. Imagine standing in what looks like the floor of a valley. The ground is solid. You look in every direction and see only uphill slopes. It appears you're at the bottom. But there is a fog in front of you, and if you walked through the fog and looked down, you would find that the valley you're standing in is not the real valley floor. It is a shelf, a ledge, and below the ledge is a drop that makes the Grand Canyon look like a crack in a sidewalk. This is the electroweak vacuum instability. The mass of the Higgs boson, precisely measured at CERN to be 25·9 GeV, combined with the mass of the top quark, places the universe in a regime that theoretical physicists call metastable. Not stable, not unstable, metastable. It is a word that sounds almost safe and is in fact deeply alarming. Metastable means the current configuration could persist essentially forever, or it could collapse. Not because anything hits it, not because of any experiment we run or any weapon we build, just because of the fundamental quantum mechanical probability that somewhere in the universe, in some cubic centimeter of space, a fluctuation in this Higgs field happens at just the right magnitude to push it over the edge of the ledge. When that happens, if it happens, a bubble forms. A bubble of true vacuum, where the Higgs field drops to its actual minimum energy. Inside that bubble, the Higgs field has a different value, which means the masses of all particles are different, which means the forces between them are different, which means atoms as you know them are not the stable configurations anymore. Chemistry as we know it does not work in that bubble. Biological molecules do not fold, nuclei do not hold. The structures that make you do not persist in the new physics. The bubble expands at the speed of light. It does not slow down, it does not stop. It converts every cubic centimeter of universe it passes through into a region where the physical laws have fundamentally changed, and where our kind of matter cannot persist. You would never see it coming. It travels at the speed of light, which means it arrives at the same instant as any information about it. You would not feel it approaching. You would not hear it. You would not have time to process what is happening. The laws that allow your neurons to fire, that allow your atoms to bind, that allow your molecules to hold their shape, they would simply stop applying, mid-thought, mid-breath, mid-heartbeat. With no warning, no sound, no pain, the universe would continue, just with different rules, just without everything you recognize as real. CERN is measuring this stability problem with extreme care. Every refined measurement of the Higgs boson properties, its mass, its self-coupling, its coupling to other particles, is a data point in the stability calculation. And what they find, every time, is that the numbers sit in the same zone, metastable, not catastrophically unstable, not safely stable, right on the ledge, within the error bars that straddle the boundary between the two fates. Here is what makes this particularly uncomfortable. The stability calculation assumes we know all the particles that contribute to the Higgs potential, all the particles that interact with the Higgs field and modify its quantum corrections. We know the particles in the standard model, but we just established that there is at least one sector of physics we don't know about, the dark sector, the extra-dimensional physics, the unknown force that is making the muon wobble and the B mesons die wrong. Those unknown particles also couple to the Higgs field. They also contribute to the quantum corrections that determine the shape of the Higgs potential. We have not included their contributions in the stability calculation. We cannot include them because we don't know what they are. The stability calculation we have performed is incomplete, and we don't know whether the unknown contributions push us towards stability or toward the edge. Every unanswered question at CERN is not just a scientific mystery. It is a variable in the equation that determines whether the vacuum holds. The seventh crack, the signal from the other side we have been building toward this. Every anomaly we've looked at, the decaying B mesons, the wobbling muons, the missing energy, the extra dimension hints, the antimatter asymmetry, the metastable vacuum, all of it circles around a central question that the data keeps pressing us toward, closer and closer, until it becomes impossible to ignore. Is there something on the other side? Not in a mystical sense, not in a religious sense, in a rigorous mathematical, experimentally testable sense. Is there another sector of reality, another region of the quantum field, that our universe is coupled to? A sector with its own particles, its own forces, its own structure? A mirror world that exists in the space as ours but interacts with it only faintly, only at the highest energies, only at the smallest distances. The data says yes, not conclusively, not at 5 sigma, but the convergence is undeniable. Multiple independent experiments, multiple independent anomalies, multiple independent theoretical frameworks, all pointing at the same blank space on the map, all suggesting that reality has more rooms than we've been willing to admit. Let me explain specifically what CERN's phaser experiment found, because it is the most direct evidence of this convergence. Phaser, the forward search experiment, is a small detector installed in an unused tunnel 480 meters from the main Atlas collision point. It was designed specifically to catch long-lived particles that travel far from the collision before decaying. Most experiments look at what happens right at the collision point. Phaser looks at what happens nearly half a kilometer away. It is hunting the things that get away, the things that travel far before they finally give up and reveal themselves. In 2023, Phaser reported the first direct detection of neutrinos produced at a particle collider, a historic first. But in subsequent running, Phaser also began searching for what are called dark photons. A dark photon is to a photon what a dark sector is to our sector. It would be the force carrier of a dark electromagnetic force, a version of light that belongs to a parallel world. If a dark sector exists, it may have its own version of electromagnetism, its own version of light, its own version of the force that holds electrons to atoms and allows chemistry. Dark photons are predicted to occasionally oscillate into regular photons at a specific rate. If Phaser can detect these oscillations, if it can catch a dark photon briefly converting into a detectable photon, it would be the first direct evidence that two electromagnetic fields exist in nature simultaneously, one we live in and one we don't. Phaser has not confirmed dark photons, but it has set limits on where they are not, narrowing the allowed parameter space to a specific region. And the region that remains, the region where dark photons could still be hiding, is precisely where the muon anomaly and the B meson anomaly are pointing. 3 independent measurements, 3 different experiments, 3 different physics quantities, all converging on the same corner of the same map. Now add the moidal experiment, also at CERN, which is hunting for magnetic monopoles, particles that grand unified theories predict must exist. Moidal's null results and limits are consistent with the same energy scale. The SND experiment, which detected collider neutrinos alongside Phaser, is finding evidence that neutrino interactions at this energy are subtly different from predictions. And Atlas has released preliminary results from searches for long-lived particles, objects that travel a significant distance inside the detector before decaying, that show a handful of unexplained events in exactly the topology that dark sector models predict. The signal is not confirmed, it is not 5 sigma. It is right now a handful of events in a dataset of trillions, but they are in exactly the right place, not scattered randomly across the detector, not appearing in channels where backgrounds are high, appearing in precisely the configuration that theorists calculated years ago, before the data was collected, based on the physics of dark sector particles created in proton collisions, traveling through the Atlas detector and decaying back into standard model particles at the far end. When the data lands in the predicted distribution, you are not looking at noise, you are looking at a signal. What the scientists are not saying publicly here is something you need to understand about how physics works at the highest levels. Scientists are trained to be conservative. They are trained to understate, not overstate. They are trained to present anomalies as curiosities, not emergencies. They are trained to say we observe an interesting deviation rather than the foundations of physics may be cracked. This is not dishonesty. It is intellectual discipline. It is the correct approach when the stakes are this high. You do not want the people mapping the structure of reality to be prone to panic. But there is a gap between what the papers say and what the physicists say at dinner. There is a gap between the careful language of a peer-reviewed journal and the conversation in the corridor of a CERN building at midnight. That gap has been widening for 3 years. In 2011, when the OPERA experiment appeared to show neutrinos traveling faster than light, the reaction was careful skepticism. The result was an error, a loose cable in the timing system. It was caught, corrected. The system worked, but the system worked quickly and cleanly because there was no other anomaly pointing in the same direction. OPERA was isolated, a single outlier in otherwise clean data. The anomalies we are discussing are not isolated. They have been accumulating for a decade. The B meson violation began appearing in 2014 and has grown more significant with every additional dataset. The muon G2 discrepancy was first measured at Brookhaven in 2001 and confirmed at Fermilab with 6 years of additional data. The missing energy anomalies have persisted across multiple LHC runs at different energies. The vacuum metastability has become more precisely uncomfortable with every refinement of the Higgs and top quark masses. Each one individually could be a systematic error, a calibration artifact, a subtle mistake in the theoretical prediction. Physicists are trained to believe that before they believe new physics, and they are right to be. But collectively, the anomalies form a pattern. They are not scattered randomly across the theory space. They cluster around a specific energy scale. They are all consistent with physics that involves new particles in the mass range of a few hundred GeV to a few TeV. They all point toward the same sector of the parameter space. They all suggest the same fundamental diagnosis. The standard model is missing something, and that something has a specific mass and a specific coupling structure that we are beginning to triangulate. Patterns in physics are not coincidences. Patterns are messages. And the message being sent from the LHC data to the theoretical physics community is this. The standard model is not incomplete in small correctable ways. It is incomplete in deep structural ways. There are forces and particles and possibly entire sectors of reality that we have not yet discovered. And the energy scale at which they hide is either just above what we can currently probe, which means the next generation of colliders will find them, or it is precisely where we are looking right now. And precisely where we are looking right now is the scenario that wakes physicists up at 3 in the morning. Because if new physics is hiding at the 13.6 TeV scale, the scale the LHC currently runs at, then we should be seeing it clearly, not as hints, not as persistent soft deviations. We should be producing new particles in large numbers and watching them decay into visible signatures. The fact that we are not seeing it clearly, but are seeing these strange, soft, suggestive hints means one of three things. 1. We are unlucky, and the anomalies are all flukes that will go away with more data. 2. The new physics is there, but it interacts so weakly with our sector that it barely leaves a mark, which is exactly what dark sector models predict. The new particles exist. They are produced in collisions. But they couple to our sector so faintly that most of them escape undetected, leaving only the faintest residual distortions in decay ratios and magnetic moments and energy budgets. 3. The new physics is there, but we are not interpreting the data correctly. Our theoretical framework is missing something fundamental. We are asking the wrong questions. We are running searches based on the wrong signal topologies. We are sitting in the middle of the most important dataset ever collected and reading it through the wrong lens. Option 3 is the one nobody wants to sit with, because option 3 means the revolution may be hiding not in more data but in a different way of thinking, a different mathematics, a different organizing principle. It means the answer might already be in the data, has been in the data for years, waiting for someone to develop the conceptual framework to see it. Like trying to decode a foreign language using the wrong alphabet. The text is there, the information is there, but until you find the key, it looks like noise. The machine we are building next CERN is not done. In 2028, the LHC will begin its final upgrade to become the high-luminosity LHC. The goal is not to increase the collision energy, it will remain at 13.6 TeV, but to increase the collision rate dramatically. The HL-LHC will accumulate 15 times more data than the entire current total of all previous LHC runs combined. 15 times. Every analysis that currently sits at 3.8 sigma will either grow into a 5 sigma discovery or dissolve into background. There will be nowhere for the anomalies to hide. The statistics will become overwhelming. Either they are real or they will go away. But CERN has already approved something beyond the HL-LHC. It is called the Future Circular Collider. It is planned to be 91 kilometers in circumference, more than 3 times the size of the LHC. It will sit in a new tunnel beneath the Alps, built at a cost that will likely exceed 20 billion euros. And it will accelerate particles to 100 trillion electron volts. That is 7 times the current world record. Think about what that energy scale means physically. At 100 TeV, we would be recreating conditions from the first 10 to the minus 18 seconds after the Big Bang, a billionth of a second after the moment of creation. We would be probing distance scales of 10 to the minus 20 meters, 10 times smaller than a proton. We would be accessing physics that has never been accessible to any laboratory in human history, on Earth or anywhere else. At that energy scale, if extra dimensions exist at the scale that the Randall-Sundrum models predict, the FCC will produce Kaluza-Klein gravitons in enormous numbers, not search for traces of them. Create them routinely and watch them decay. If dark sector particles couple to the standard model at the rates suggested by the LHEB and Fermilab anomalies, the FCC will create them by the billions. If the Higgs field's self-coupling has the value that determines vacuum stability, the FCC will measure it to the precision needed to say definitively whether we are sitting on stable ground or on a ledge. The FCC is scheduled to begin its first phase, an electron-positron collider using the new tunnel, in the early 2040s, with the full proton-proton machine following in the 2050s. That is a generation away, which means we are currently in a specific historical window that physicists will one day look back on as one of the most important periods in the history of science. We are in the window between the anomaly and the revolution, between the crack in the wall and the moment someone walks through it. between the persistent, suggestive, maddening hints and the definitive discovery that changes everything. The Michelson-Morley experiment of 1887 is the closest parallel. That experiment failed to detect the luminiferous ether, the invisible medium that physicists believed light travelled through. It failed so precisely, so carefully, so undeniably that it demonstrated the ether did not exist. But the failure had no explanation. The data was inconsistent with every known physical model. It was an anomaly without a resolution. For 20 years it sat in the literature as an unresolved puzzle, occasionally debated, often set aside. Then Einstein published special relativity in 1905, and the anomaly was not just resolved. It was revealed to be the most important experimental result in a generation. The absence of the expected was the presence of something far more profound. We are in that window. We have the anomalies. We are waiting for the framework that will make them make sense. And unlike Einstein, who was working alone in a patent office in Bern, the people working in this window have access to the most powerful tools humanity has ever built. 10,000 collaborators, petabytes of data, global computing networks capable of processing 1 trillion events per second, machine learning algorithms trained to find patterns in noise that human analysis would never see. The revolution, when it comes, will not take 20 years, it will come fast. The implications we are not ready for, so let's say it happens. Let's say the HL-LHC confirms a dark sector. Let's say they find the particles that explain the muon anomaly and the B meson violation and the missing energy. Let's say they crack open the wall between our sector and the sector next door. What are the implications? What does it actually mean to find that reality has a parallel structure we've never accessed? Most people imagine it will be like finding a new continent, a new territory to explore, new resources, new possibilities. We expand our map and continue as before: progress, discovery, scientific journals and Nobel Prizes, and a new generation of textbooks. But that framing fundamentally misunderstands what a dark sector discovery would mean. And I want to explain why, because the misunderstanding is not trivial. It is the difference between thinking, this is an addition to what we know, and understanding that it is a restructuring of the foundations of what we know. Our current understanding of reality is a specific set of rules that applies to everything we have ever touched, seen, tasted, smelled, built, destroyed, loved, or hated. The Standard Model, general relativity, thermodynamics, chemistry, biology, all of it sits on the assumption that these rules are complete in the domain of everyday experience. They are the physics of everything you have ever interacted with. If there is a dark sector, the rules are not complete. There are forces operating in this room right now that we cannot feel. There are particles passing through your body this second that your body cannot detect. Not just neutrinos, we know about those. Dark sector particles. Particles that carry a force your body has no organ for. A force that has been operating on every atom of matter in the universe since the beginning of time, and that we have literally never noticed. How do you recalibrate your sense of reality when you discover that reality contains a layer you are completely blind to? It is not like discovering a new continent. It is like discovering that you have been walking through walls your entire life and never knew it. That the walls were there, physical and real, and you were simply not dense enough in the right way to feel them. That an entire civilization could be standing on the other side of the wall you are leaning against right now, and you would not know, because the only forces that could carry information between you are so weak that they might as well not exist at the energies of everyday life. Dark sector physics does not just add pages to the textbook. It adds an entire library that exists in a language we have never learned. A library that has been sitting next to ours for 13.8 billion years, and we are only now building the instruments capable of noticing the shelves. The question that cannot be unasked here is where we arrive at the question that physicists are careful never to say out loud in press conferences, but that haunts every corridor at CERN. If there is a dark sector, a parallel set of forces and particles that is structurally similar to our sector, does it have a dark chemistry? If dark electromagnetism is real, and its force-carrying particle is the dark photon, then there is a binding force in the dark sector, analogous to the electromagnetic force that binds electrons to nuclei in our sector. That force can in principle create dark atoms. Dark atoms can in principle form dark molecules. Dark molecules can in principle undergo dark chemistry. Does dark chemistry allow for dark biology? This is not a crazy question, it is a logical extrapolation of the physics. Our form of life is built on electromagnetic chemistry, on the ability of electrons to form covalent bonds between atoms, on the quantum mechanics of electron orbitals, on the specific energy scales at which chemical bonds form and break and rearrange. All of that flows from the existence of the electromagnetic force and the specific value of the fine structure constant that governs its strength. If the dark sector has an analogous force, all of that scaffolding could in principle exist there too. over billions of years, in a medium we cannot see, in structures that pass through our own structures without leaving a mark. And if dark life exists, it faces exactly the problem we face. It is blind to our sector. Its instruments cannot detect our particles. Its telescopes see through us without registering us. Its most sensitive measurements show tiny, inexplicable anomalies in decay ratios and magnetic moments. Anomalies that its physicists puzzle over and cannot explain with their own version of the standard model. You see where this is going. What if the anomalies we are seeing are not just a passive consequence of dark sector physics existing? What if some fraction of them are the unavoidable physics waste product of a technological civilization operating in the dark sector, generating high-energy collisions or advanced processes that bleed energy and particles into our sector? The way our civilization bleeds radio waves and infrared heat signatures into space. Not messages, not intentional communication, just physics exhaust. The inevitable byproduct of doing things that involve high energies and produce missing energy signatures. We spend $13 billion building detectors to find the faintest whisper of new physics in the LHC data. We treat every 3 sigma deviation as a landmark worth publishing. We comb through trillions of events looking for the single anomalous one. What if something on the other side of the dark sector wall has been doing the same thing, for longer, with better instruments, and has already found us? What if the anomalies in our data are not questions we are asking the universe? What if they are the universe's way of telling us the answer to a question someone else has already asked? The silence that is not empty. We've talked about what CERN is finding. We haven't talked about what CERN expected and didn't find. This is equally important, perhaps more so. In 2012, when the Higgs boson was discovered, the theoretical physics community was not just celebrating the completion of the standard model. They were celebrating because they expected something else to come with it. Every major theoretical framework that predicted the Higgs also predicted additional particles appearing at roughly the same energy scale. Supersymmetry predicted a superpartner for every known particle, the supersymmetric partner of the top quark, the supersymmetric partner of the Higgs boson. An entire shadow zoo that would explain dark matter, solve the hierarchy problem, and elegantly extend the standard model to higher energies. Supersymmetry was not a fringe theory. It was the dominant paradigm in theoretical physics for 30 years. Thousands of papers, hundreds of careers, Nobel laureates advocating for it. When the LHC turned on, the expectation in the community was not whether supersymmetric particles would be found. It was which ones would be found first. They were not found. Hundreds of independent searches, every possible decay channel, every possible production mechanism, every possible mass range accessible to the LHC. Superpartners were not found at 1 TeV. Not at 2 TeV, not at 6 TeV. The silence is complete, and the absence is now so well established that the simplest versions of supersymmetry, the ones that were supposed to solve the hierarchy problem at accessible energies, are definitively ruled out. The same is true for the simplest large extra dimension models, and the simplest dark matter candidates in the weakly interacting massive particle framework, and the simplest versions of Technicolor. Model after model, prediction after prediction, the LHC has returned clean negative results in channels where the predicted new physics should have appeared. This pattern has a name. Physicists call it the nightmare scenario, the scenario where the LHC finds only the Higgs and nothing else, where every extension of the standard model is wrong simultaneously, where there is a vast desert between the TeV scale and whatever true new physics exists at much higher energies. But here is the thing about the nightmare scenario. If the desert is real, if there truly is nothing between 1 TeV and whatever energy scale the next physics lives at, then the fine-tuning problem of the Higgs mass gets worse, not better. The hierarchy problem demands an explanation. The absence of supersymmetry doesn't make that demand go away. It makes it more urgent. Why is the Higgs mass where it is? What is stabilizing it? What is protecting it from the enormous quantum corrections that should be driving it to the Planck scale? If supersymmetry isn't the answer, something else must be. And that something else must be real, physical, and accessible to experiment. Otherwise we have a universe that is fine-tuned without a mechanism, which is a confession, not an explanation. And then the anomalies started appearing, the B meson violation, the muon G2, the missing energy. These are not the clean, sharp signatures of a new particle produced with a specific mass and a specific decay chain. They are soft, indirect, persistent deviations. They are the kind of signal that dark sector particles with very weak couplings to our sector would produce. Present enough to distort precision measurements, absent enough to evade direct detection searches. The nightmare scenario and the anomalous hints are not contradictory, they are consistent. They both point toward new physics that interacts so weakly with our sector that direct production searches come up empty, while precision measurements show systematic deviations. The absence of the expected is not an absence of the real. It is a redirection. Nature is not cooperating with the theories we built. It is pointing somewhere harder to reach, somewhere deeper, somewhere that requires not just a bigger machine, but a different way of thinking about what we are measuring. The shapes in the data, the soft hints, the persistent deviations, the missing energy, are the composting that way. The problem of the scale, let's talk about a number that reframes everything. 14 mils and mils and thousand. 14 trillion electron volts, the maximum collision energy of the LHC. In human terms, it is enormous. In terms of energy scales in the universe, it is a starting point, a first step. The Planck scale, the energy at which quantum gravity becomes important, at which space and time lose their smooth structure, is 10 to the power of 28 electron volts. The ratio between where the LHC currently operates and where the deepest physics of reality lives is approximately 10 to the power of 15, a quadrillion. 1 followed by 15 zeros. We are never going to build an accelerator that reaches the Planck scale, not with any conceivable engineering, not with any technology that extrapolates from what we have. The energy requirements would dwarf the output of stars. The cost would exceed the GDP of civilizations. It is not a question of funding or political will. It is a question of physical scale. The universe simply does not permit that kind of concentration of energy in a machine built by matter. Which means there is a question at the heart of particle physics that we must answer honestly. Can we understand the deepest structure of reality from the tiny slice of energy we can access? Can we read the architecture of physics from its low-energy shadows? The history of physics says yes, sometimes. Sometimes the deepest physics leaves legible footprints at low energy. Sometimes the patterns in precision measurements at accessible scales encode information about the structure at inaccessible scales. The Standard Model itself was built from measurements taken at energies far below the scales where its parameters are unified. The success of the electroweak theory at LEP energies encoded information about physics at the unification scale. The anomalies at CERN might be exactly this kind of footprint. Kaluza-Klein gravitons escaping into extra dimensions at LHC energies would be a direct imprint of physics at much higher scales. Dark sector particles coupling faintly to our sector would be a low-energy shadow of a sector that might have its own rich structure at higher energies. The muon G-factor, measured to 11 decimal places, is precisely the kind of observable that can be sensitive to physics at much higher masses through quantum loop corrections. We are archaeologists brushing dust from a surface. We have uncovered a corner. The corner's geometry tells us the object is large and regular in ways that suggest it was made by something. We cannot see what it is. We cannot excavate it fully, but the corner is real. And the geometry of the corner, if we read it carefully enough, will tell us what we are dealing with. That is the bet that CERN is placing with each run, each analysis, each precision measurement, that the low-energy footprints are legible, that the physics is kind enough to whisper about itself at energies we can reach, that the corner of the object we can touch contains enough information to infer the shape of the whole. So far, it appears to be correct. The anomalies are consistent, they converge, they point. The question is whether we are wise enough to follow where they point. The unstable atom at the center of everything. Let us talk about something that no one wants to talk about and everyone should. Let us talk about what you are standing on in the most fundamental physical sense. You are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. Quarks are bound together by gluons, the carriers of the strong nuclear force. Electrons orbit nuclei because of the electromagnetic force. Every stable atom in the periodic table is a balance between these forces, holding together through a specific set of parameters, existing because the constants of nature have the values they have. Change the mass of the up quark by 10%. Protons become unstable. No protons means no hydrogen, no water, no organic chemistry, no life. Change the electromagnetic fine structure constant by 1%. The energy levels of atomic orbitals shift. Carbon does not form in stellar cores via the triple alpha process. No carbon means no organic chemistry, no biology, no us. Change the strong coupling constant significantly. Protons and neutrons do not bind into nuclei. No nuclei means no complex atoms. No complex atoms means no chemistry. No chemistry means nothing. The universe is fine-tuned. The constants of nature sit at values that, with minimal variation in most directions, would produce a universe with no complexity, no structure, no life. This observation has a name in physics, the anthropic coincidence, and it is one of the deepest, least resolved problems in all of fundamental science. Why do the constants have the values they have? Why are we on this narrow ridge where chemistry is possible, where stars can burn stably for billions of years, where DNA can encode information, where neurons can wire themselves into networks capable of asking these questions? CERN is directly probing this. Every precision measurement of the Higgs boson mass is a measurement of one of the most critically fine-tuned parameters in nature. Every measurement of the top quark mass contributes to the calculation of vacuum stability. Every measurement of the strong coupling constant refines our understanding of why nuclear physics permits the elements that permit chemistry. And every measurement comes back in the same uncomfortable zone, not randomly distributed within the physical possibility space, sitting right at the values that permit complexity, right at the edge of stability in the Higgs potential, right at the threshold where the triple alpha process that makes carbon in stars barely works. The universe is not configured randomly. It is configured at the edge of possibility, at the minimum set of constants, consistent with the existence of things capable of asking about constants. There are several ways to interpret this. The multiverse offers one. If there are 10 to the 500 universes with different constants, it is not surprising we find ourselves in one that permits life. Only in such universes could observers exist to find themselves. The anthropic principle as a selection effect. Not evidence of design, but evidence of selection from a large ensemble. Fine-tuning without a constructor. Selection without a selector. A vast uninhabited landscape with one tiny island of livability. And we are on the island because there is nowhere else for us to be. CERN cannot test the multiverse directly, but it can test the conditions of fine-tuning. It can measure whether the vacuum is truly metastable in the way multiverse models require. It can probe the coupling structure of the Higgs to see if there are stabilizing contributions from physics we haven't found. It can look for the spectral signatures of the extra dimensions that create the landscape of universes in string theory. Every measurement is a vote, cast by nature, in the language of data, on the question of why anything exists at all. What you are standing on, let's return to the ground beneath your feet one final time before we close. You have been walking on it your whole life. You trust it implicitly. You can feel it. It is solid. It holds you. You have never had reason to doubt it. But everything we have discussed tonight describes a ground that is stranger and less simple than you imagined. A ground that sits on a Higgs field that is metastable, stable enough to have lasted 13.8 billion years, but sitting on a ledge rather than the true floor. A ground threaded through at every point by dark sector particles that pass through the atoms of the Earth without stopping, carrying a force your body has no way to detect. A ground permeated by gravitational influence from dimensions that may be real, but that nothing in your daily experience has ever given you reason to believe in. A ground whose existence depended on one extra particle of matter surviving in a billion at the moment of creation. A cosmic asymmetry whose cause we do not understand. You feel solid because the Higgs field has the value it has, because the fine-tuning held through 13.8 billion years, because the asymmetry was just enough, because the dark sector passes through you so faintly that you cannot feel it, because the vacuum has not yet found a fluctuation large enough to tip it off the ledge. You feel solid for the same reason a lake surface looks solid from a distance, because you don't have the resolution to see the churning at the molecular level, but the lake is churning. And underneath the apparent stability of the standard model, underneath the equations that describe the atoms of your body, there is a physics that is more complex, more contingent, more layered than any textbook has ever captured. Here is the honest summary of what CERN's data is telling us. 7 distinct signals: the B meson-lepton violation, the muon G-factor anomaly, the missing energy deficit, the extra dimension hints from Kaluza-Klein physics, the CP violation excess in antimatter asymmetry, the Higgs vacuum metastability, and the dark sector convergence across Phaser and Atlas and LHCb individually qualify as serious anomalies and collectively qualify as a systematic pattern. A pattern that has been building across multiple experiments over more than a decade. A pattern that gets stronger with more data, not weaker. A pattern that converges on the same energy scale, the same theoretical frameworks, the same blank space in the map of physics. The blank space is not empty, something is there. It does not have a name. It might be a dark sector with its own forces and its own structure. It might be extra spatial dimensions through which gravity leaks and particles can escape. It might be something so different from our existing theoretical frameworks that we will need genuinely new mathematics to describe it. But the pattern is real, the data is real, the convergence is real, and we are one generation of accelerators away from finding it. The last comfort we have, if you are feeling a specific kind of vertigo right now, a dizziness that comes not from the room spinning but from your model of the room being wrong, then you are feeling exactly what physicists feel when they sit with this data at the end of a long day. Let me offer you what they offer themselves. Not false comfort, not a soothing narrative about how everything will be fine. The real thing. Every time in history that physics discovered its current model was incomplete, the discovery did not destroy the world. It did not unmake the phenomena the old model described. Newton's mechanics were incomplete. but bridges built using Newton's equations still stand today. Classical electromagnetism was incomplete, but the radio waves it predicted still carry voices across oceans. The Standard Model is incomplete, but the atoms it describes are still here. Your body still works, the chemistry still runs, the stars still burn. Incompleteness does not mean falseness, it means narrowness, it means there is more. And there is more is not a terrifying sentence. It is the most exciting sentence in the history of human thought. It is the sentence that has followed every major discovery. It is the sentence that opens the next chapter. It is the sentence that means the story is not over and that the best parts may not have been written yet. The machine in the mountains of Switzerland is still running. The protons are still colliding 11,000 times per second in 4 cathedral-sized detectors. The data is still streaming, 1 billion events per second, filtered and processed and analysed by the most sophisticated computing network in the history of science. And somewhere in that data, in the precise wobble of a muon's magnetic moment, in the missing corner of an energy budget, in the asymmetric decay of a B meson, in the handful of anomalous, long-lived particle events in the Atlas inner detector, the universe is leaving a message. The message is not a threat, it is not a warning, it is an invitation. It says, you have been in the entrance hall, there is a door in the back, you've been feeling the draft from it for years. Now you're close enough to see it. We are learning how to read what is written on the door, and when we do, nothing will look the same again. The weight of the knowing there is a concept in information security called a zero-day vulnerability. It is a flaw in a system that exists before anyone knows about it. Before it is discovered, the system appears perfectly secure. Nothing is visibly wrong, but the flaw is there, real and operational, waiting. It has always been there. The security was always an illusion. The flaw was just undiscovered. What CERN is finding might be the zero-day vulnerability of our model of reality. A gap in our description of physics that has existed since the moment the universe began. Not a flaw in nature, but a flaw in our knowledge of nature. A region of the physics that we had mapped incorrectly because the tools available to us had never been precise enough to see the error. A blank space on the map, dressed up as understood territory. The gap does not threaten the atoms in your body. The dark sector particles that pass through you are not hurting you. The extra dimensions that gravity leaks into are not pulling you apart. The vacuum metastability is not imminent. Nothing you have learned tonight requires action. You can set this information down and go back to your life, and nothing about your daily experience will be different. Except your picture of what your daily experience is made of. And that, to be honest, is the most valuable thing a piece of knowledge can give you. Not a change in behaviour, a change in perception, a shift in what you see when you look at your hand. The atoms there, trillions of them, held together by forces you now understand are a visible layer of a deeper physics, are more remarkable than you thought this morning, more contingent, more improbable, more precisely arranged in a configuration that required 13.8 billion years of physical history, a mysterious asymmetry in the first microsecond of time, a Higgs field sitting on a ledge, and a planet in a solar system in a galaxy that happened to form from the 1 in a billion excess of matter that survived. You are the result of every good measurement the universe made, every correctly set constant, every held stability, every survived fluctuation. The machine in the Alps is currently trying to read those measurements, to understand the mechanism behind them, to map the physics one layer deeper. You don't need to be afraid of that. You need to be astonished by it. The final measurement, we are near the end. But there is one more thing to say. It is the thing that matters most. Physics has always advanced by being willing to be wrong. The history of science is not a history of correct theories. It is a history of successive approximations, each one better than the last, each one covering more of reality, each one incorporating the previous one as a special case and extending beyond it. Newton was not wrong about gravity. He was right about gravity in the regime he could measure. Einstein extended him. Quantum mechanics extended classical mechanics. The Standard Model extended everything that came before it. What is coming next will not destroy what came before. It will contain it. It will explain the anomalies. It will show why the muon wobbles the way it does, and where the missing energy goes, and why matter survived the first microsecond. And when the explanation comes, it will look obvious in retrospect. The way special relativity looks obvious after you understand it. The way quantum mechanics looks obvious once you accept that particles are waves. The people working at CERN right now are not working in the dark. They are not confused or defeated by the anomalies. They are working with the quiet, focused intensity of people who know they are close to something important. The intensity that happens in hallways at midnight and in emails sent between time zones and in papers submitted to ArXiv at 3 a.m. The specific quality of attention that comes when you are no longer exploring randomly but following a thread. They are following a thread. We spent $13.25 billion on this machine. We spent 50 years building the theory it was designed to test. We found the last missing piece of the puzzle we thought we were completing. And then the machine kept running, and the data kept showing us that the puzzle was inside a larger puzzle, that the room we had mapped was a room inside a building we hadn't entered, that the universe we thought we understood was a surface. And below the surface, detectable only at 13.6 trillion electron volts, only in the milliseconds after a collision, only in the discrepancy between predicted and observed, only in the precise ratio of muons to electrons in billions of B meson decays, was something that has been there the whole time. Something that does not have a name yet. Something that is real. Something that is waiting. The machine is still running. The data is still coming. And somewhere in 30,000 trillion collisions, the universe is leaving a message. We are learning how to read it. And when we do, nothing will look the same again. The dark matter problem. Why have researchers failed? Let's spend more time on dark matter. Because the failure to find it directly is not a minor footnote. It is the loudest silence in modern science. And the way CERN is reinterpreting that silence, the way the LHC anomalies are forcing physicists to rethink what dark matter even is, changes the entire nature of the problem. Here is the problem stated clearly. Every galaxy we have ever observed rotates at the wrong speed. Not slightly wrong, dramatically wrong. When you measure the rotation curve of a spiral galaxy, the speed at which stars orbit the galactic center as a function of their distance from it, the standard model prediction is specific and confident. Stars near the center, where most of the visible mass is concentrated, should orbit fast. Stars near the edge, far from the mass concentration, should orbit slow. This is Kepler's laws applied to galactic scales. It is the same physics that makes Mercury orbit faster than Neptune. It has been verified in our own solar system to extraordinary precision. But when astronomers measure actual galaxies, the outer stars don't slow down. They maintain roughly the same orbital speed all the way to the edge of the observable disk. The rotation curve is flat where it should fall. And this is not true for one galaxy or 10 or 100. It is true for every galaxy that has been measured in sufficient detail, every spiral galaxy, every elliptical galaxy where the measurement is possible, everywhere. The only explanation consistent with gravity is that there is more mass in those galaxies than we can see, much more. A vast distributed halo of matter extending far beyond the visible stellar disk, providing the gravitational glue that holds the outer stars on their orbits. Matter that emits no light at any wavelength we can detect. Matter that interacts gravitationally, but in no other way we have been able to measure. Dark matter. The gravitational evidence is not limited to rotation curves. Gravitational lensing, the bending of light from distant objects by gravitational mass in the foreground, independently confirms dark matter halos around galaxies and galaxy clusters. The Bullet cluster, two galaxy clusters that have passed through each other, shows the dark matter halo separated from the ordinary matter, passing through the collision undisturbed while the gas collided and slowed. The large-scale structure of the universe, the filaments and voids of the cosmic web spanning hundreds of millions of light-years, could not have formed in 13.8 billion years without dark matter providing the gravitational seeds for structure formation. The acoustic peaks in the cosmic microwave background independently encode the presence of dark matter in the early universe. Every independent method of detection, using completely different physics and completely different instruments, arrives at the same conclusion. Dark matter is real. It is 5 times more abundant than ordinary matter, and we have never directly detected it. For 30 years, the leading hypothesis was the WIMP, the weakly interacting massive particle. The theoretical motivation was compelling. Supersymmetric extensions of the standard model naturally predicted heavy neutral particles at the TeV mass scale that would have been produced in the right abundance in the early universe, and would today be travelling through space interacting only gravitationally and through the weak nuclear force. Detecting them would require placing a large mass of ordinary matter in a quiet underground laboratory and watching for the rare nuclear recoil when a WIMP passed through. Experiments were built. Deep in mines in South Dakota and Ontario and Italy and China, tanks of liquid xenon were cooled to near absolute zero and shielded from cosmic rays. Germanium crystals were suspended in dilution refrigerators. Bubble chambers were filled with superheated fluid. Each generation was more sensitive than the last. Each year the limits were pushed down. Each publication ruled out more of the parameter space. The WIMPs were not found. The most recent generation of experiments, Lux Zeppelin in South Dakota, Panda X40 in China, Xenont in Italy, have reached sensitivities so extreme that they are approaching the neutrino floor, the irreducible background from standard model neutrinos that no experiment can reduce further. They have not seen a WIMP signal. They have not seen a hint of a WIMP signal. The LHC was also supposed to produce WIMPs directly. In proton-proton collisions at TeV energies, WIMP should be created in pairs and escape the detector as missing energy, sometimes in association with a jet of quarks that would tag the event. The signature is called monojets. Atlas and CMS have conducted monojet searches with the full LHC dataset. They have set world best limits on WIMP production cross-sections. They have not found WIMPs. The WIMP miracle, the remarkable coincidence by which the predicted relic density of a weakly interacting massive particle naturally matched the observed dark matter density, has not translated into a detection. Now look at this in the context of the LHC anomalies. The muon anomaly and the B meson anomaly both suggest new physics involving particles that couple very weakly to the standard model sector. The missing energy anomaly suggests particles escaping the detector by propagating into directions inaccessible to the detectors. Both of these are consistent with a dark sector, a parallel set of particles and forces that interacts with our sector only faintly. In the most natural dark sector models, dark matter is not a WIMP. It is dark matter, matter that belongs to the dark sector, held together by dark electromagnetic forces, structured by dark chemistry, moving through our universe the way we move through it, occupying the same space, following the same gravitational laws, but coupled to our particles by forces so weak that direct detection experiments will never see it. You cannot catch dark sector dark matter in a xenon tank, because dark sector dark matter does not interact with xenon. It does not interact with protons. It does not scatter off atomic nuclei. The direct detection paradigm assumes dark matter couples to standard model particles through the weak force. Dark sector dark matter couples through a dark force that ordinary matter has no way to access. This is why the silence of the dark matter searches is, paradoxically, exactly what the LHC anomalies are pointing toward. The absence of WIMPs is not a failure of the dark matter hypothesis. It is a refinement of it. It is nature telling us that dark matter is not where we were looking. It is in the sector next door. The sector that the muon anomaly and the B meson anomaly and the missing energy are showing us. The 30-year WIMP hunt was not a failure. It was the elimination of the wrong hypothesis, and eliminating wrong hypotheses is exactly what experimental physics is supposed to do. It clears the map, it narrows the territory, and the territory that remains, once the WIMP parameter space has been ruled out, points directly at the dark sector. This is where the search is going next. This is what the HLLHC is designed to probe. This is the blank space on the map that 7 anomalies are collectively pointing toward. The hierarchy problem, the deepest embarrassment in physics. There is a problem in theoretical physics so deep and so uncomfortable that it has been the central motivation for new theories for 40 years. It is called the hierarchy problem, and understanding it is essential for understanding why the LHC anomalies matter beyond their individual experimental significance. The Higgs boson has a mass of 125 GeV. This is a measured fact confirmed at CERN to high precision. But in quantum field theory, the mass of the Higgs boson is not simply the parameter you write into the Lagrangian. It receives quantum corrections from every particle that couples to it. Every virtual particle loop that briefly appears and disappears in the quantum foam of the Higgs field. These corrections add to the bare Higgs mass and shift the physical mass that gets measured. The corrections are large, extremely large. Each fermion that couples to the Higgs contributes a correction proportional to the square of its mass. The top quark, the heaviest known fermion with a mass of 173 GeV, contributes a correction to the Higgs mass that is roughly of order the top quark mass squared divided by some reference scale. If the standard model is valid up to the Planck scale, the scale of quantum gravity at 10 to the 19 GeV, then the quantum corrections to the Higgs mass are of order 10 to the 38 GeV squared. The physical Higgs mass squared is about 15,000 GeV squared. For the physical mass to be 125 GeV, the bare Higgs mass and all the quantum corrections must cancel to 34 decimal places. Not approximately, exactly. A 34 decimal place cancellation between parameters that, in the standard model, have absolutely no reason to be related. This is fine-tuning so extreme that it strikes most physicists as physically meaningless. A theory that requires 34 decimal places of accidental cancellation to produce an observed mass is not a natural theory. It is a theory that is hiding something. It is a theory that has a mechanism we have not yet found, a mechanism that enforces the cancellation automatically, without requiring hand-tuning. Supersymmetry was supposed to be that mechanism. Supersymmetry introduces a superpartner for every standard model particle. Each fermion's contribution to the Higgs mass correction is cancelled by its bosonic superpartner and vice versa. The cancellation is automatic, built into the mathematical structure of supersymmetry. The fine-tuning problem dissolves. But the superpartners were not found at the LHC. Supersymmetry, as a solution to the hierarchy problem at the TeV scale, is effectively ruled out. Large extra dimensions were another proposed mechanism. In the ADD model, gravity spreads into extra dimensions, and the Planck scale in our brain is lowered to the TeV scale. The hierarchy problem disappears because there is no hierarchy. The fundamental scale of gravity is the same as the electroweak scale, and the apparent weakness of gravity in our 4 dimensions is a geometrical artifact of the extra dimensions. In this model, the Higgs mass is naturally of order the TeV scale with no fine-tuning required. The LHC has searched for the signatures of large extra dimensions, Kaluza-Klein graviton production, virtual graviton exchange, missing energy signatures from gravitons escaping into extra dimensions. The direct signatures have not been found at the predicted scale. But the anomalies that have been found, the muon G2, the missing energy deficit, the dark sector hints, are consistent with a variation of this scenario in which the extra dimensions are slightly smaller or the coupling slightly weaker than the simplest models predicted. The hierarchy problem is not solved, but the anomalies are pointing at the energy scale and the type of physics that would solve it. The pattern of deviations in precision measurements is exactly the kind of imprint you would expect from physics that addresses the hierarchy problem at a scale just above the current LHC reach. The problem is real, the solution is in the data, we just haven't decoded it yet. The cosmic story we are telling ourselves. There is a way of looking at everything we have discussed that I want to offer before we close. Not a scientific perspective, a narrative perspective. Because the LHC anomalies are not just data, they are a chapter in a story that has been building for a very long time. The story goes like this. For most of human history, we believed we understood what things were made of. First it was earth, air, fire, and water. Then it was atoms, indivisible, eternal, the last unit of matter. Then atoms turned out to be made of electrons and nuclei. Then nuclei turned out to be made of protons and neutrons. Then protons and neutrons turned out to be made of quarks. Each discovery pushed the floor of reality one level deeper. Each level was described by a theory that was exactly right within its domain and exactly incomplete beyond it. The standard model is the current floor, the deepest level we have mapped, the description of quarks and leptons and bosons that has worked with extraordinary precision for 50 years. It is the best theory in the history of science in terms of predictive accuracy, and it is incomplete. It is the floor that has a basement, the basement that has anomalies pointing to a sub-basement. We are currently standing on the floor, feeling the vibrations from below, trying to understand what is down there. Every generation of physicists has stood in this same position. Every generation has been told by some that the physics is essentially finished, that the remaining questions are details, that the fundamental picture is settled, and every generation has eventually found the basement. We are that generation. We are the generation that built the machine to test the final theory and found that the final theory has a crack, that the crack is real, persistent, and systematic, that the crack is telling us something. Here is what makes this moment different from all the previous moments of discovery. We are not just finding that our current theory is incomplete. We are finding specific, quantitative evidence that the incompleteness has a structure. The anomalies are not scattered randomly. They cluster, they converge, they point at the same energy scale, the wobbling structure, the same type of new physics. In previous revolutions, the anomaly was often a single, isolated experimental result that refused to fit the existing theory. The perihelion of Mercury, the photoelectric effect, the ultraviolet catastrophe, single anomalies that force theoretical revision. We have seven independent measurements across multiple experiments, each individually significant and collectively overwhelming, all pointing in the same direction. This has not happened before in the history of fundamental physics. The convergence is telling us something important. The new physics is real, it is specific, and we are close to it. We are at the edge of the next level. The door to the basement is in front of us. We can feel the air coming under it. We just need to figure out how to open it, and we will. The machine that thinks about itself here is a thing that is almost impossible to fully absorb if you sit with it long enough. The universe has been expanding and cooling and evolving for 13.8 billion years. In that time, stars have formed and exploded and distributed heavy elements across galaxies. Those elements have condensed into planets. On at least one of those planets, chemistry has produced biology. Biology has produced nervous systems. Nervous systems have produced the capacity for asking questions about their own origin. And those nervous systems, these extraordinarily improbable arrangements of atoms, have built instruments capable of recreating the conditions of the universe's first microsecond and studying what happens at that energy scale. The universe is thinking about itself, not metaphorically, literally. The matter of the universe has arranged itself, in one small corner of one galaxy, into a configuration capable of building the Large Hadron Collider and asking what matter is made of. This is not a small thing. This is the most extraordinary fact in the known history of the cosmos. In 13.8 billion years of physical history, across 100 billion galaxies, each containing hundreds of billions of stars, we know of exactly one place and one moment at which organized matter has become sophisticated enough to interrogate its own fundamental structure. And that organized matter, that specific improbable arrangement of atoms, those 10,000 physicists from 100 countries, is currently finding that its own fundamental structure is more complex than it thought, that the equations it wrote are right but incomplete, that there is more, that the universe, when it examines itself with sufficient precision, finds something it did not expect. There is a beauty in this that the dry language of physics papers does not capture. The anomalies at CERN are not just scientific puzzles. They are moments in the universe's examination of itself. Moments where the matter of the universe, arranged in the shape of instruments and mathematicians and data analysts, finds that it does not yet fully understand what it is made of, and commits to understanding it. That commitment, that choice to follow the data wherever it points, to hold the anomalies honestly, to publish the deviations even when they don't make sense, to keep running the machine and refining the analysis and building better models, that is not just good science. It is the universe's way of taking its own measure. We are the universe's tape measure. We are the universe's mirror. We are the specific configuration of matter that the universe has produced to examine itself. And the mirror is showing a crack, not a flaw in the mirror. A crack in the surface of reality itself, visible only because the mirror is precise enough to see it. The revolution that is coming, let me be direct about what I think will happen in the next 20 years. Not what I hope. What the data is telling us will happen if the anomalies are real. The HLLHC will begin full operation in 2028. It will deliver 10 times the data of every LHC run that came before it combined. The B-meson-lepton universality violation, currently at 3.8 sigma, will either grow into a 5 sigma discovery or wash out into background. The Muon G2 result from Fermilab will be cross-checked against new theoretical calculations of the hadronic vacuum polarization, the most significant source of theoretical uncertainty in the prediction, and the experimental and theoretical values will either converge or diverge in a way that makes the situation unambiguous. The missing energy anomalies will either accumulate into a coherent picture of a specific new particle or scatter into the noise of a better understood background. If the anomalies are real, if the dark sector is real, if the extra dimensions are real, the HLLHC will make discoveries, not hints, discoveries. The kind of sharp, clean 5 sigma signals that fill papers with excited language and press conferences with crowded rooms. The kind of discoveries that generate Nobel Prizes and open new fields of research. And then the future circular collider will begin. At 100 TeV, the physics landscape changes completely. The energy scale where the hierarchy problem lives becomes directly accessible. The Kaluza-Klein graviton spectrum becomes directly measurable. Dark sector particles with couplings many orders of magnitude below what the LHC can probe become producible in large numbers. The Higgs self-coupling, the parameter that determines vacuum stability, gets measured to the precision needed to make a definitive statement about the fate of the universe. The FCC era will not be a continuation of the LHC era. It will be a different kind of physics. The LHC was built to test the standard model and find the Higgs. The FCC will be built to map whatever comes after the standard model, to understand the structure of the dark sector, to test the geometry of extra dimensions, to determine whether the vacuum is stable or metastable to the precision that the question demands. The revolution is coming. The anomalies are its advanced signal. The HLLHC is its first confirmation. The FCC is its full fruition. The physicists who are currently in graduate school, learning to analyze LHC data and build theoretical models, will be the physicists who confirm the discoveries, who map the dark sector, who measure the geometry of extra dimensions, who answer the question of vacuum stability. They will look back on this moment, on the period of persistent, maddening, unexplained anomalies, as the prologue, as the years when the data was whispering what it would eventually shout. And they will understand, in a way that we can only begin to, exactly what the whisper was saying. The fine-tuning we cannot explain. Before we arrive at the final word, there is one more truth the LHC data is pressing on us. One more layer of strangeness beneath the 7 anomalies. One more place where the data does not just show that our theory is incomplete, but shows that the universe itself is configured in a way that demands explanation. It is called fine-tuning, and it is the most philosophically destabilizing thing in modern physics. Consider the electromagnetic force. It has a specific strength, described by a number called the fine structure constant, approximately 1137. This number determines the size of atoms, the energy of chemical bonds, the wavelengths of light that biological eyes evolved to detect, the energy scale of every chemical reaction in every living cell on Earth. If the fine structure constant were 1100 instead of 1137, atoms would be smaller, chemistry would be different, and the specific biochemical reactions that support life as we know it would not work the same way. If it were 1/200, atoms would be larger, chemical bonds would be weaker, complex molecules would not hold together reliably at the temperatures where liquid water is stable. Life, as we understand it, requires the fine structure constant to be within a relatively narrow window around its actual value. Not exactly 1/137, a small variation could be tolerated, but order of magnitude changes would make life impossible. The standard model does not explain why the fine structure constant has its value. It is a free parameter, a number that must be measured and entered into the equations by hand. The theory gives no reason why it is what it is. It simply is. Now extend this to all the constants. The strong coupling constant, the Higgs vacuum expectation value, the cosmological constant, the mass ratios of the quarks, each one is a free parameter. Each one has a measured value. Each one sits in a range that is compatible with complex chemistry and biology. The probability of randomly selecting constants that all sit in their respective life-permitting ranges, if the constants are truly independent and the ranges are small, is extraordinarily small. Not zero, but small enough to require explanation. This is the fine-tuning problem, and it is exactly the problem that the LHC anomalies are probing. When CERN measures the Higgs boson mass to higher precision, it is measuring one of the most fine-tuned quantities in nature. When it measures the top quark mass, it is measuring the parameter whose value most strongly influences vacuum stability. When it studies the Higgs self-coupling, it is studying the parameter that determines whether the fine-tuning of the vacuum is stable, or whether the vacuum is slowly sliding toward a different configuration. The anomalies we are seeing, the deviations in B-meson decays, the muon magnetic moment, the missing energy, may themselves be clues to the fine-tuning mechanism. In models where extra dimensions exist, the hierarchy problem is naturally solved and the Higgs mass is naturally light, without requiring enormous cancellations. In dark sector models, the coupling between the sectors can naturally explain some of the apparent fine-tuning of the standard model parameters. The fine-tuning problem and the LHC anomalies are connected. They are different angles on the same mountain. The anomalies show us where the new physics is hiding. The fine-tuning problem tells us why the new physics must be there. Because a universe with parameters precisely set to permit complex chemistry and biology, with no mechanism enforcing those parameters, is a universe that is hiding something. And the something it is hiding is exactly what the LHC is beginning to see. A deeper layer, a more fundamental framework, a physics that makes the fine-tuning natural. That explains why the constants have the values they have. That shows us the mechanism behind the coincidences that make your existence possible. We are reading that mechanism's fingerprints in the data, one anomaly at a time. The thing that waits here is the last image I want to leave you with. Somewhere in the universe, on a scale we cannot observe, at an energy we cannot reach, in a sector of physics we have not yet accessed, there is a structure, a physical structure governed by mathematical laws, existing whether or not we know about it. It has been there since the beginning. It shaped the conditions of the Big Bang. It influenced the formation of the first stars. It has been pressing gently on every muon that has ever existed, adding a tiny unmeasured contribution to its magnetic wobble. It has been briefly appearing in every B-meson decay, nudging the ratio of products by a fraction of a percent. It has been taking a small slice of energy from every high-energy collision and carrying it somewhere our detectors cannot follow. It has been waiting, not patiently in the sense of choosing to wait, simply existing, being real, being physical, being part of the total description of what the universe is made of. And in a tunnel beneath the Alps, in a ring of superconducting magnets that took 20 years to build, the matter of the universe has arranged itself into a configuration precise enough to finally see the fingerprints of that waiting thing. Not clearly, not yet, in the form of a 3.8 sigma deviation in a decay ratio, a 4.2 sigma wobble in a magnetic moment, a systematic missing energy deficit in specific collision topologies, a handful of anomalous long-lived particle events in the inner detector, fingerprints on the glass. The next generation of physicists will follow those fingerprints. They will build the HLLHC and collect 15 times more data. They will build the FCC and access 7 times more energy. They will run analyses we have not yet designed, using mathematics we have not yet developed, looking for signatures we have not yet imagined. And they will find what is leaving the fingerprints. They will open the door that the anomalies are pointing toward, and when they open it, they will find exactly what every generation of physicists has found on the other side of every door that anomalies have ever pointed toward. Not the end of questions, but the beginning of a richer set of questions. Not the completion of the map, but the discovery that the map has a new continent. Not the universe we thought we understood, the universe we actually live in. The universe is not done showing us what it is made of. It has never been done. Every machine we have ever built to probe its structure has found something we didn't expect. Every generation that has declared physics finished has been wrong. The standard model was not the end, it was a door. And the data from CERN, 7 anomalies, 7 cracks, 7 independent measurements pointing at the same blank space, is the sound of that door opening. Something is on the other side. And for the first time in human history, we have built instruments sensitive enough to hear it breathing. The machine is still running. 11,000 loops per second. 4 cathedrals of measurement recording the aftermath. 1 billion events per second, filtered through the most sophisticated computing infrastructure in the history of science. Somewhere in the data, in a deviation that is not yet 5 sigma, in a missing corner of an energy budget, in the precise ratio of 2 particles that should be equal and aren't, the universe is making a point. It has been making this point for a decade. We are finally listening carefully enough to hear it. Keep your eyes open. The next line of the story is already in the data. We just haven't decoded it yet.